All right. So in my last lecture, I'm going to change topics a bit, as I mentioned last time, and talk about unsupervised learning. So this is a bit of a bad name, and I'll come back to that. But most of what we talked about thus far was thinking about learning functions that map inputs to outputs. The outputs could be continuous if you're talking about regression. They could be discrete classes if you're talking about classification. But almost always it was trying to find some function or conditional distribution that maps an x to a y. And today I want to focus on constructing models of data x where there is no y. All you have is samples x. And there are various reasons why you might want to do that. And depending on the reason, then you can come up with an objective function that you use to fit your model. And that's part of why calling it unsupervised learning is not necessarily the best term. It's not that we're just doing whatever we want. Unsupervised, we're deciding what we want the model to do and then supervising it in the sense of telling it to do what we want it to do. So these days, the term unsupervised learning, although it's still pretty common, is a little bit out of fashion, and you hear terms like self-supervised learning or predictive learning that are a little bit more popular, or at least growing in popularity. So let's before we actually talk about any models, let me talk about the kinds of things that you might want to do with a model of just inputs x. So one thing that is common if you're working on a problem in science is you actually want to take the model and look at its structure, and maybe you can understand something about the data by looking at the model itself. If you think this is a good model of the data, you can understand something about the data by doing that. If you are working in a more applied domain, you might do something like denoising, where you have a noisy sample that has been corrupted, and you would like to get back to the nice, perfect sample that didn't have the noise. So your model might be asked to do something like that. You might be able to use a stage of unsupervised learning, even if you do have labels y, as information to put into a model that then you can use to do classification subsequently. So I mentioned this briefly yesterday when we were talking about neural networks, that there was a time roughly 10 years ago when people were doing this to find good ways of initializing the parameters of a neural network. So there are lots of different things that you might want to do. Another one could be if you learn a model and you think it's a good model, then you can sample from that model and generate new samples that you think are good. So another term for these kinds of models in that context is generative models, because you're generating samples. Okay. So the place I wanted to start, and actually before I do that, let me mention that I'm going to give you an overview of a couple of different types of approaches, and there are some approaches that are relatively popular in the theoretical biophysics world right now, and then there are approaches that are more popular in the machine learning world, and these are somewhat distinct, and I'm going to try and tell you about both of those and tell you which ones are popular in which world. And I think the reasons for the different degrees of popularity is due to them focusing on different kinds of questions. As I was saying, unsupervised learning involves many different kinds of tasks that you might want to achieve, and the questions that are being asked in biophysics are different than the ones that are being asked at Google DeepMind. So just because you don't see DeepMind doing something doesn't mean that you shouldn't be interested in it. Okay, so the place I want to start, and I'm almost positive that this has already been talked about, is maximum entropy models. So have we already heard about that in this lecture, or in this course? Let me just briefly go through it, because the framework is useful. So the idea in maximum entropy models is I want to come up with a distribution, P of x, a model distribution, that can predict certain properties of my data, but doesn't add any extra structure that I don't want built into it. So roughly what you do is you ask the model to match certain statistics. So you say, I want to match the average value of this, the average value of that, that I see in the data. I want my model to reproduce that. And then I want the distribution that has the largest entropy otherwise. And so you write down some Lagrangian that you say, I want to say I'm going to minimize it, so I'll maximize, I'll minimize minus the entropy. And then you say I have a bunch of observables that I'm going to call, let's see what notation I can use, that I'm going to call F. So let's say I can compute these observables in my data, and then I have a model that is going to make a prediction on what these things are doing. And I add a bunch of Lagrange multipliers so that I match these statistics, and then I add a normalization. And let me know if I'm going too fast through this, because I assume you've already seen this. So what you do is sorry?
What is theta, right? Lagrange multiplier.
Yeah, so these are Lagrange multipliers. I normally call them lambda, but I'm going to generalize these to just parameters, so I'm going to call them theta. SP is just the entropy. Of the distribution, yeah.
I guess just maybe you'll get there, but is there a cost function or not? Like, so before you start out with, you have you training your function. You're learning what the function is by minimizing some cost to maximizing some.
Yeah, we'll get there. There will be a cost function. So this is going to motivate a form for a model, and then we'll have a cost function that achieves this. So here there are a bunch of parameters, these thetas.
You can think of this as the second term as like the cost function, right?
You want to find the function p that minimizes this. So this is a cost function that now you have to solve by setting the values of all these Lagrange multipliers, and there's a different cost function that is going to be useful in practice for actually doing that, which is.
But so there's a sense in which there's a training, because you have a value of observables.
Mm-hmm. Yeah. So this is data. Right. Yeah, exactly. This is actual data.
Sense is like I was thinking that somehow if it's unsupervised, that there's no training step.
Yeah, so that's why I was trying to emphasize that this term unsupervised is misleading,
Okay.
and it's only unsupervised in the sense that people use supervised to say I have pairs of x and y, and y tells me what I care about in x, and if all I have are x's, nothing is telling me a priori what I care about. So this becomes a modeling choice to decide what are the FIs that I care about. And I'll get back to this in a minute.
Okay.
So if you take the functional derivative here and set it equal to 0, with respect to p of x, you get log p of x plus 1 from the entropy. You get two other terms. Rearranging, you get something that looks like a Boltzmann distribution. And I've changed variables from gamma to the normalization z. And the reason I show this is to say that so this gives you the functional form, but now you still have to find the values of theta. And I'll come back in a minute to how you go about doing that. This little derivation just shows you that the idea of maximizing entropy subject to certain constraints of matching certain statistics in your data motivates a model P of x of this form. And it's important to keep in mind that although this is the least constrained in the sense of maximum entropy model subject to the constraints of f, you've chosen the FIs that you think are important. So they're, in some sense, it's the analog of the y's. Like there weren't any, so you decided, I want my model to match certain things. There are things that are actually directly derivable from the x's. They're not something that's correlated with it, so it's a little bit different. But you've given your own sort of supervision in a sense to the model, in the sense of saying, I want the model to match the average values of certain things. So you've made a modeling decision here. And how do you go about choosing those f's? It's not always obvious. If you know something about your data, if you know what matters, you should pick those things and make sure you get those things right and have it not worry about the other things. If you don't know what matters, then often what people do is to choose the quantities f in the data that they think they can estimate well. So again, this is from a data set. And if the data set is not so large, or you choose f's that are complicated, it may be that you don't have enough data to actually pin down what the average value is with small error bars. That would be a bad quantity to choose. So you might choose things that you can estimate well from the data. And that motivates this functional form. But, OK, does that make sense? So how do you actually go about finding the values of these parameters? In principle, what you should do is you should make sure that the average values of the f's match the data. And I guess in principle you can do that, but I don't know how helpful it is. I don't know how to calculate those things. And you might anticipate from statistical physics that you should take a derivative with respect to the conjugate parameter, and then I'll tell you the average value, and you should match that. And that is what you do, but I want to give you a different perspective on where that comes from, thinking about models like this in general. So this is going to go, another term, maximum likelihood of energy-based models. And the idea is, here you were motivated to think about fitting a model to your data X of this form by wanting to match the average values of these quantities F. But you could have just been handed some model that was of this form, e to the sum over some parameters times some operators or functions of your data. And I don't know where it came from. That's just the model that I want to fit. And I'm going to call that an energy-based model because this looks like a Boltzmann distribution with some parameters. And I would like to fit that model to my data. And what does fit mean is the first question. So in the case of maximum entropy, we said we want to match these statistics. If I dissociate myself from that motivation of where this model comes from, I just have a probability distribution that I want to match to my data. I need to say what it means to match, and this is where people often use the idea of maximum likelihood. So we talked about this in the second lecture, right? And the idea essentially is to say I can think about the the log of the probability of some sample in my data, and I can average this with respect to all of the samples. So I can just plug in all of my samples, look at the average log probability that my model predicts, and I can find the parameters in this model. So maybe I should start putting a sub theta here. I can find the values of theta that maximize this log probability. And if I have a model that is in this form here, then that is just going to look like minus the average value of some energy function that is what's in the exponent, minus log z. Okay? And our goal is to maximize this with respect to theta.
But also theta has to be bigger than the averages there?
So,
Or you're not doing it?
so it's going to be the case that doing this is the same as matching the thetas, matching the f's. I'll show you in a second. So how do we maximize this? Well, we can go back to day 2 and do gradient ascent on this, right? So let's take the gradient with respect to the parameters theta. And what you get if you, so just to make sure we're clear, I'm writing this as an e to the energy. So if we take the gradient, then if I call this sorry?
Is your definition minus the energy?
Oh, sorry. Yeah, sorry.
I mean, so that guy is just the entropy, right?
Um,
Quantity you just defined.
that would be the case if the data and the model matched perfectly. But in general, they don't. So what we'll compute is minus the derivative with respect to some particular parameter. And here you get, let's see. I have a minus sign off from how I wanted it to be. You'll get something modulo a minus sign, my apologies, that is fi of x from the data, again, because this is average over the data. And then we'll take the derivative of log z here, and this will give us the average value of f in the model, right? So I'll write that as average of f in the model. So you can see that following the gradient, again, modulo a minus sign that I mixed up, whenever I am not matching the average value of f, I'll have some direction to move. And then once I match all of these statistics, then I will be at a 0. My gradient will be 0. So maximizing the likelihood of an energy-based model is the same as matching the statistics of these operators that are conjugate to the parameters that you want to fit. Is this clear? So I think this is actually a good place to give a little bit of an aside on whether maximum likelihood itself is a good idea, and whether the likelihood is something that you should want to fit. Probably so let me. I don't think I've introduced the Callback library divergence, but have you heard this before in other lectures? Yes? Okay. So maximum likelihood is equivalent to minimizing the Callback library divergence from the data distribution to the model distribution, p theta. And so what is this DKL? It's p data of x log p data of x divided by p model of x, or p theta I'm calling it. And what you do in practice is you treat this data distribution, and this integral is just the empirical samples. So you just plug in the samples here, and you lose this, and there's a term which is the entropy of the data, which we don't know anything about, and we don't get to control it, so we can ignore it. And then what we have left is p data log p model, which is this thing that we're working with. So this is the direction of KL divergence that corresponds to maximizing the likelihood. And what that means is if you have, let's say, a data distribution that looks like this. So this is p data. Then your model really doesn't want to put probability mass where there is no data, because you'll get a divergence here on the bottom. Sorry, the other way around. It doesn't want to not put mass where there is data. So what it ends up doing is it's happy to have something that looks kind of like this, where it sort of smooths out the data more than it should, and it's not really being penalized for having mass out here where there is no data. That's not exactly true. It is penalized a little bit because you're fitting a normalized distribution, and if you put data where there is if you put model where there is no data, the normalization affects you a little bit, but it's a really weak penalty. On the other hand, you could imagine looking at the DKL the other way. Model to data. And if you do that, then if you had a situation like above, then the model really doesn't want to put mass where there is no data. Do that badly. It will sort of potentially focus itself. Let's say you're fitting only a Gaussian or something. It'll focus itself on one of these peaks. So you can get very different behavior when you have KLs in different directions, and maximum likelihood corresponds to putting data in the first slot of the KL. The fact that the model is not really, yeah?
Do not symmetrize the KL divergence, and then you would get something in the middle?
Yeah, so you can symmetrize, and that's something called the Jensen-Shannon divergence. And that's potentially a good idea. And in fact, one of the most popular generative modeling ideas in the past 5 years is called generative adversarial networks, or GANs, which you might have heard of or seen these, like thispersondoesnotexist.com, these images, or this Airbnb does not exist, or whatever. The motivation, or one of the motivations behind GANs, is the fact that this reverse KL is useful in some sense. The problem is you can't actually compute it, because then you have to do an integral over x, and you have to query what the data believes the probability is of some sample where there is no data. So you can't actually compute this. And what GANs do are they found a neat way to get the juice of sort of the Jensen-Shannon divergence without actually computing these things. And the idea is to have two models. One is a generative model like our P of theta here, piece of data here. The other one is a discriminator that tries to distinguish between samples that are real and samples that are generated by the model. And then if you have a situation like this, where the model is generating samples sometimes that are way different than the data, the discriminator will be able to say, hey, that's not right, and then it'll pull it back. So one of the central ideas motivating GANs is, in fact, getting some of the juice of both of these directions of KL, even though you can't actually compute this one. Does that make some sense? This is just an aside. For everything that I'm going to talk about today, I'm going to be interested in essentially maximizing the likelihood.
You say this is, if you could, this would be preferred over the maximum likelihood?
No, not necessarily. They just have different behavior.
This doesn't have this adverse effect of smoothing over the distribution. So what's
Right.
the negative? What is
The,
efficiency of this one?
so in this case, the objective is doing something that's called mean seeking, and this is doing sort of mode seeking. And in this case, if your model is not flexible enough to fit all the wiggles, it will sort of focus on the mode, and it'll do a good job there. So if you were just generating samples, all those samples would look reasonable, but there's a whole other set of behavior in your data that you're missing completely. So getting both is useful. Okay. Right. So yeah, this is the basic idea. In everything that I'm going to talk about, we're going to worry just about maximizing the likelihood and not worry about these issues. And I haven't seen too many applications of GANs, say, in biophysics. I don't know if anyone has any examples that I've missed. But this is one of the reasons that I'm not focusing on it. Not that I don't think it's interesting and important, but just that I haven't seen it being applied, whereas energy-based and Maxent models trained via maximum likelihood is much more common.
Virus structure.
Really?
They won a virus structure competition using GANs.
Interesting. Okay. So maybe I should have talked about it. Okay. So this was just an aside. So the idea of using these energy-based or Maxent models has been around for a long time, and there are different kinds of Fs that are chosen. The most common is to choose a set of Fs that correspond to the average values of each x, and then the pairwise correlations between each x. And then what you end up getting is something that looks like an Ising model in a sense, where you have fields and biases on all of your degrees of freedom and interactions. I'm not going to go into that too much because I assume that you've already seen that. Where I wanted to go instead was to try and motivate why, if you're using models like this, you might want to think about adding latent or hidden variables as well. So let me imagine, and just make sure, how many of you have seen like Maxent Ising models? And how many of you have seen that in this this course? So it was actually not talked about. Interesting. Okay. So oftentimes you'll see the energy function here chosen to be something like something like this, and the x's correspond to some binary. Yeah.
Sorry, just before you get into it, I'm just curious, are there more general maximum entropy models that are not exponential? So you'd have some term in the cost function that's some functional of the probability that's not the entropy. if you have the constraints as moments, but you could imagine
No, but maximum
other
entropy.
constraints.
Any maximum entropy model will be exponential, right? It's just going to be.
But you're saying you want to constrain something that's not an average value?
Yeah. Does
Well-
that make any sense?
What do you want to constrain?
Some functional on the probability.
No, but it's still going to be.
It'll still-
You're going to do P log P. You're going to differentiate. You get log P equal to something on the right hand side, which will make P equal to an exponent of that something on the right hand side. Right? Whatever you're going to put there, if you are doing max end on Boltzmann-Shannon entropy, you will get an exponent with something. It might not be properly defined if you decided to, let's say, do third order moments or something like that. But if it's defined, it's exponential.
Only if you have moments in the cost function. What if you have a functional?
Still,
I mean, if you have a function like log of something, right, then in that case it will not be exponential.
Just wondering.
Like if you put a p squared or something here.
Yeah.
I think that's right. Have you seen anyone do this?
No. But I was kind of thinking there are other forms than Shannon entropy. I don't know, there's presumably other formulations of these kinds of constraint problems. So I'm just curious.
Mm-hmm.
I guess what I was really getting at was maybe is there any way to expand the family beyond the exponential family of distributions in some principled way? So I was curious about.
Possibly. I'm not good at thinking in real time with 80 pairs of eyes looking at me, but so I'm gonna limit myself to.
There's a million different sort of Thales entropy, Rene entropy, max end models, which maybe will do what you want.
That would be maximizing a different entropy, presumably.
Yes. I mean, there's a usual problem that if you actually you want to get also a normalizable distribution, and it's not very easy to get a normalizable distribution with constructions like that, right? You also want to make sure that whatever you are maximizing has a single minimum, right? When you are doing it with expectation values and log p, which is convex, you are guaranteed a single minimum. If you are going to have log p and then p squared on top of that, it's probably not a single minimum, and then you are screwed, right? That's
Yeah. Related to that, this is maybe a good time to say this. So one of the reasons why these models are, more of interest on the scientific side than these days on the applied side is that that learning them, first of all, you don't get a normalized distribution, nor is it normalizable. So you don't have z of theta here, and the way you learn it involves computing these expectation values in the model, and that requires doing sampling, so Monte Carlo sampling, to estimate this. And you have to get the estimate for whatever values of parameters you have at this time, and then update it. So every time you take a step, you have to take a bunch of samples, and this is a really slow process. And in general, if you want to learn really big models with a huge number of parameters with really high dimensional data, that's going to be too slow, and it's going to limit you. And what I'll tell you about in the latter part of the lecture is one of the approaches that gets around doing this sort of slow sampling. Yeah, and it's worth emphasizing that again, in the end, what you get is the values of these theta i's that you can put into this form here, but you don't know the z. And that is problematic for a couple of reasons. One of them is, what if you have two different models and you want to compare which one is a better model? So what I would have said is, well, we trained with respect to an objective function, which was the likelihood. Let's keep some of our data separate and have a held out data set to test on, and then we'll look at the log probability of the data on that test set in the model. The problem is you can't actually get that normalized log probability because you don't have the z. And if you just have one model, okay, it's a constant, I don't really care. But if I want to compare which model, this one or this one is better, I need that normalization to be able to see which one is making better predictions on the held out data, right? So it makes it kind of difficult to do model selection with cross-validation.
You can compare the energy distributions of both.
Say it again?
You can compare the energy distributions. If you got the energy with your model, and you can compute the energy of the
Yeah,
data.
there are certainly things you can do. I don't want to imply that there's nothing, but the standard idea of doing cross-validation of log probability is not going to work easily without getting z. And then there are other ways of trying to estimate z via importance sampling and so on. But it's involved. It would be nice if you had in hand just a normalized distribution for free where you didn't have to worry about these kinds of issues. Yeah.
So like going back to the very beginning of your first lecture where you were trying to fit, let's say, some data with some model. So in that context, like, you didn't have a target Y. So how would you pick these observables, these average FRs?
Yeah, that's a decision of the modeler. Nothing in the data necessarily is going to tell you what those Fs should be. You have to choose that based on what you think is interesting in the data, or more often than not, what you can actually estimate from the data. But yeah, certainly that's something that you're adding on to create to choose what model to fit. And certainly, if you have a nested model class, and as you add more and more parameters, you're going to be able to fit more and more data increasingly well. So you'll be able to get a higher likelihood on that data set by adding more parameters. So you'll tend to overfit, and worrying about cross-validation is important for that reason, for knowing which model is better.
Is there a concept of bias and variance here as well, or not?
I think so. I haven't actually thought about it in the case of unsupervised learning. There must be. Yeah, the intuitions hold over, certainly.
Like there's an optimal number of thetas or something.
Right. Yeah. Okay. So.
Can I comment on this?
Yeah.
So for example, if you are trying to infer this parameter theta, like for example, corresponding to the covariances between observed spins, like constraining, let's say, pairwise interactions, then we know that in a marching posterior spectrum basically theorems tells us that not all of the covariances that you observe are actually statistically significant, right? There's going to be a cutoff beyond which they are insignificant. And so if you are trying to constrain more of these parameters than is allowed by the marching posterior constraints, then you're going to be fitting delta functions effectively in the distribution rather than large-scale features.
And so one thing that you can do to mitigate this, so you had asked, I think, a couple days ago that, okay, so maybe you want to be careful and not use too many parameters here so that you don't overfit and just fit delta functions on your data. You can do what we did in the second lecture and add a term up here, plus lambda times some penalty on that regularizes, the L2 norm of the parameters or whatnot. So you can do the same kind of thing that you did before here by adding it. Okay, so a common kind of choice for these Fs is to have the Fs be linear and bilinear combinations of whatever your data is. Oftentimes it's neuron activities or amino acid sequences or whatever. And what I wanted to say here is let's imagine that I take this Jij matrix, which is telling me about the interactions between these degrees of freedom, and do like a like an SVD on them, and write this as a sum over some index mu, wi mu, wj mu, so that this term, becomes a sum over ij mu, vi, wi mu, wj mu, x, sorry. Then it turns out that this form of the energy function corresponds to what's called the Hopfield model. I don't know if, give me a show of hands if you've heard of or seen the Hopfield model before. Okay, great. So the idea from Hopfield's paper in 1982 was to have a bunch of patterns that you would like to be stored as memories, and if you give a corrupted version of that pattern, then you could do sort of zero temperature Monte Carlo, just go downhill in energy from some initialized corrupted pattern and until you reach the bottom of a well, and that will be the model's reconstructed version. So this is an example of that utility of unsupervised learning for doing denoising. Okay. What we can do, however, is I can take this this energy function and think about the probability of x, and what I want to do is actually get rid of the interactions between these x's by doing sort of a Hubbard-Stratonovich transformation, or just introducing some extra degrees of freedom that, when I integrate them out, give you back these interactions. Yeah.
Can I complain a little bit? Because
Yeah.
it's not an energy function, right? There's no dynamics.
What's not an energy function?
I mean, you just call it E.
Okay.
It's not, I mean, how is it an energy? It's not like the dynamics sort of actually take you to, you don't have dynamics.
There's no dynamics.
So
This is
in what sense is this an energy? It's just log P.
minus log p. Yeah.
Minus log P. So I've always been confused about this.
I mean, if
In what cases am I allowed to think of this as
if I give you an equilibrium static problem with an energy, I haven't told you any dynamics either.
True.
Like I can run Kawasaki dynamics, I can run whatever Glauber dynamics. I have to tell you the dynamics of the system. This is just telling me about the probabilities of different states in some equilibrium ensemble.
Only if you know that you started with equilibrium. This is not necessarily an equilibrium ensemble.
It's a distribution that corresponds to the equilibrium distribution when you where E was the energy function.
So what do you think change if you just call it pseudo energy and just move on?
Sure. I mean, yeah. There's no physics here.
That's what I wanted to get him to say.
But your idea is you're going to try to optimize AI and JIJ to best fit the data according to, let's say, some maximum likelihood or something. Is that fair?
Yeah. So that's sort of what we were doing here. I think it's a terminology thing. Michael was talking about how in his field and in physics certain things are very confusing. This is another one of them. But it's true that there is no dynamics, and maybe you're commenting on this now because of my statement about Hopfield. That was just an aside. I don't actually need to think. So Hopfield's procedure was not just to construct an energy function, but then to also tell you a dynamics for moving on that energy landscape. I don't actually need that. Okay, so what I want to do is write this as having as if we had a bunch of extra degrees of freedom I'm going to run out of space. I'm going to write this over here. So I have a bunch of auxiliary degrees of freedom, h mu's, that are Gaussian, and when I integrate them out, I get back, this should be x. Sorry? Okay. When I integrate them out, I get back this form of these interactions, right?
So somehow you're assuming GIJs are unfrustrated. Like, when you write them in terms of these W's?
Writing them in this sort of outer product way.
Like if I go around like a lattice model, I go path.
I think I should be able to do this for, I might need a large number of mu's here, but I think I should be able to do this for any GIJ matrix. So for the Hopfield model, you write this where mu is a small number, and when or not a small number, but it's smaller than some value, and then you get something that has a different flavor than a full spin glass. But then when you have enough of them, it becomes the full-blown thing. I think that's right. So essentially what we did here is we wrote this as integrating out some degrees of freedom of some e to the minus energy on, keep writing v. Some energy function that depends on both the actual data that we have and some hidden things that don't actually exist. And then we integrated them out, and we got our p of x. And this shows you that you can reconstruct the same kinds of models that involve direct, say, interactions between degrees of freedom by introducing hidden or latent degrees of freedom and then imagining integrating them out. In this case, we didn't really gain much by doing this because this was constructed to just give you back the sort of icing model that we had before. But if you change the form of this energy function on the joint state of the actual data and the hidden degrees of freedom, then you can get models that are quite powerful. So the one that I wanted to mention, both because I've written more than 0 papers on it, and it's also been used in less than 2 though. It's also been used in also been used for modeling proteins. It's called a restricted Boltzmann machine. And the idea here is to choose an energy function that looks pretty similar, but doesn't treat the h's as continuous and Gaussian, treats them as discrete and binary. So you have something that looks like you have something that looks like this, where you have fields on your data, fields on your hidden degrees of freedom, and then you have a pairwise interaction between what did I write this here for? Between your data and your hidden degrees of freedom. So you should think about this as having a population of x and a population of h, and you allow for interactions between these populations, which is the w, but there's no interactions just between the x's or just between the h's. And it turns out that if you allow the population of h to be as large as you want, so potentially exponentially large, in the number of data in the dimension of the data, you can actually model any distribution on the data. So in practice, of course, you're not going to have an exponentially large number of hidden units, and what kinds of distributions can you match with, say, a linear number of h's is something that I don't know the answer to. But this is just to say that these models are also quite powerful. And you might ask, okay, you've told me about two very different kinds of models in a sense. There are models on the left, which are maximum entry models, and you might choose to constrain the second order statistics, and that would give rise to an Ising model like this, where I learn direct interactions between degrees of freedom. Or maybe I choose a model architecture like this, where I learn direct interactions between a population of data degrees of freedom and hidden degrees of freedom. Which one should I use? Which is the right one? And in some sense, these have very different inductive biases. At least intuitively, I can't give you anything rigorous. The kinds of data where you would want to use something like this, where you have hidden degrees of freedom that are creating via integrating them out structure and correlations in your data, would be distributions for which there are a lot of high order interactions or high order correlations that you want to sculpt. Because in principle, you can have a degree of freedom here that can talk to all of these degrees of freedom in the data, and that gives you effectively an interaction of very high order that you're kind of controlling via this W matrix. The trade-off is that you're controlling these potentially high order interactions and these lower order interactions together in some way with these numbers that you don't have independent control over them. And that's probably good, otherwise you would overfit terribly. So in general, if you have data where you think the correlations in the data are generated not necessarily via them talking to each other themselves, but due to some external cause, then a model where you have hidden degrees of freedom that generates that structure might be a better model. Does that make sense? So you can continue along this path. So the last 10 years has been the decade of deep learning, right? So are there such things as deep unsupervised models or deep generative models? The answer is yes. And you could have a hidden population who itself has a hidden population, and so on. And there are different ways that you could do this, and you can learn these models. These become things that are called deep Boltzmann machines. And there was a time around 10 years ago when people were trying to work with them a lot. They've largely fallen by the wayside in the machine learning community due to these issues that I was saying over here, that they're difficult to train. They require significant Monte Carlo-like sampling to actually train. And so while they might be expressive and useful, they're computationally inefficient relative to ideas that have come since. Okay. Right. Are there any questions about adding hidden units? You look like you have a question, Greg.
So I was wondering if you took just a simple example, like a real spin model.
Yeah.
And you applied the two. You know it's a spin model, so that model has to work. But is there any reasonable way that you can compare the two models and conclude that the hidden model wouldn't be a good description of the data?
To conclude that this would be a bad model?
Yeah.
I mean, I would advocate for the answer I've been giving, which is you should train this one, you should train that one, and then you should compare their predictions on held out data if possible. Yeah. A priori, I don't know. It depends on the data, and the only thing I can say is vaguely that these models are good when you have lots of structure that comes from hidden causes. Or you could imagine if you had a deep model here that in some sense, the way that the data is being generated in the model is through a series of steps in some sense that are controlling different scales of features and so on. So if you imagine that you had hierarchically generated data, then that would be potentially a better model than one that had just direct interactions. Okay, where I wanted to go instead of continuing down the Boltzmann machine rabbit hole is to talk about some methods that avoid these issues of sampling, but nonetheless do live within this world of having hidden or latent variables causing the correlational structure in your data. So the kinds of models I wanted to talk about are called variational autoencoders. And
Before you go on,
yeah.
can you just say, like, let's say be the model, how do you find the parameters of the model?
Right. So
What you do in maximum likelihood? Or?
yeah. So you would do the same thing as maximum likelihood. Same thing with maximum likelihood as we did here. In this case, what you get is something that is just a little bit different than what you get here, but it's sort of morally similar in that you look at the correlations between the data and the conditional activities of the H's given the data and just the correlations that are inherent in the model. So it's a flavor that is sort of like matching F's in the data and F's in the model, and then you can just do gradient descent on that. So it's you have to work it out, but you get something that is similar. In practice, when people were training these models, they found that this step of having to estimate the correlations in the model was just too inefficient, and there was a time when people were coming up with all sorts of quick and dirty ways of getting some estimate of this that, like I was saying with SGD, maybe you don't need to know the exact direction to go, but like something that is roughly in the right direction. There were quick ways of getting something useful, in particular one called Contrastive Divergence that people were using to fit this, that didn't actually maximize the likelihood, it maximized something a little bit different, but similar kind of idea.
For this model,
You literally just do this, yeah. But again, this is still this is slow. So this is the bottleneck in training this. Yeah, because you have to estimate these average values in the model for every value of the parameters that you have as you're learning. Okay, so variational autoencoders are similar to the models with hidden units that I drew over there, except that two things. We don't call hidden variables H anywhere, we call them Z. And that's canon, so they're now called Z. It's one big difference. The other big difference is that there's an arrow on the interaction. Over here, the reason these models are called Boltzmann machines is that you imagine that you have data degrees of freedom, hidden degrees of freedom. There's this energy function E of x comma h, and you allow that to equilibrate, and you find some joint distribution of x and h. In variational autoencoders, you imagine that you start with some distribution, I'll call it a prior on z, p of z, and then from p of z, we generate x with a conditional p of x given z. And that essentially defines our joint distribution on x and z. Of course, I could take any distribution and write it like this or like that. It's just we're going to be explicitly working with an object which is the conditional of data given a hidden or latent degree of freedom and the prior, as opposed to considering the joint necessarily. So imagine that you have a model like this where Z is potentially high dimensional and complicated, X is potentially high dimensional and complicated, there are certain things that you are going to want to do with a model, both once you have it and also to fit it. One of the things that you want to do is to infer the values of Z given H. Z might be a good sort of summary of the structure in your data, so you might want to know that. Maybe using Bayes' rule, you want to know what is Z once you have a sample of your data. And that's going to look like this, right? That seems fine. The problem is that this denominator here, the normalization, is difficult. So P of X is going to be, an integral over Z of P of Z, P of X given Z, right? And if Z is high dimensional and the distribution is very complicated, we can't actually do this integral. We're kind of stuck. And there are different things that people have done over the years. You could estimate this integral with importance sampling. The direction I want to go is a little bit different, and let's see. I want to write down an equation and then sort of explain what's going on. The idea is going to be that we have this model P, which has our P of Z and our P of X given Z. And in principle, there exists a P of Z given X that is consistent with that. But we can't actually access it. So what we're going to do is we're going to work with a simpler distribution, Q of Z given X, and try and make Q as close to P as possible, while at the same time fitting P to the data. Does that make sense? So this actually is intimately related to variational methods in physics and mean field theory. And I wasn't planning on going through that connection today, but it is very much similar to mean field theory, where you take a complicated distribution and you replace it with a simpler distribution, and then you try to make the simpler distribution match the complicated one as much as you can. So it turns out that there's an identity. Let's say that we have the log of P of X, and I don't know what that is because it's too hard for me to compute P of X. It turns out that I can write this as the Callback lively divergence, which we were talking about a couple minutes ago, between this distribution Q that I'm going to introduce, which is going to have some parameters, and P, plus a term, which is often called the elbow, without a W. And the elbow, it stands for evidence lower bound. Why the O in bound gets an O, but the O in lower doesn't, I don't know. It's called the elobo. I don't know. The elbow is the average with respect to this Q distribution of Z given X of log P of X given Z minus the Callback lively divergence between Q and the prior P. So there's a lot to take in here. I could derive this for you, but it's not really that interesting. You can just massage the equations, and you can find that this is just a true identity. I started with some distribution P that came from a model like this. I introduced a Q and this is just true for any Q. Now, what in the world does this mean? So I don't know what this is. This is the thing I'd like to know something about. I don't know what this is either, but this is a measure of how far off my approximation to this z given x is from the true one. And then there's another term. And luckily, the other term I can actually work with. So this term involves an average value with respect to my Q distribution, which I'm assuming is simple. It's sort of like a, if I were doing mean field theory, it would be just an independent thing or something that I can work with, right? So I can do this average with respect to the log of P of x given z. And I'm assuming that I have constructed a model such that, that I can go this way easily. Once I have a z conditioned, I can go forward like this. So imagine that P of x given z is a neural network. And in came a z, and out comes an x. And I just know how to implement that with that forward pass. And then there's a term which is minus the Callback library divergence between the Q of z given x for a particular x and just the prior P of z. So one way to understand this is this Callback library divergence is non-negative. This is one of the properties of the KL divergence. And because that's true, if I work with just this elbow term, if I know what this elbow term is, I have a lower bound on log P. And that's actually why it's called evidence lower bound, because this is called the evidence, and this is now a lower bound due to the non-negativity of the KL. So we can't actually access this, but we know it's non-negative. And we also want it to be as small as possible, because we want our Q to match the P. And one way that we can make that happen is by making the elbow as large as possible. Because this is just an identity. As the elbow goes up, this goes down, because this is just a number that we don't know. OK. So the objective then is to maximize this objective. And this is what you try to do in a variational autoencoder. There are different things that you have to do. If you hold P fixed, actually, let me go the other way. First, let's say that we hold Q fixed and we try to optimize P. That's actually pretty easy. You can just take the gradients with respect to stuff here and here. I'm not going to go through the details, but it's not too problematic. When you try for a fixed value of P to improve Q, there's a subtlety, which is that you're taking expectation values with respect to a distribution that has parameters that you want to optimize. And if you're not cognizant of that, if you imagine trying to get an estimate of this by doing taking a sample of this, that sample itself was affected by those parameters. And you need the gradient with respect to those parameters that generated the sample. So you have to do something which is called the reparameterization trick. And this is a little bit technical, so I don't want to go into it in too much detail. But what you essentially do is you rewrite the z's that come out in terms of some extra noise that doesn't have any parameters, and then a piece that the parameters here are affecting. And then from that sample, then you can take the gradient with respect to the parameters. So this is a little bit of an aside to just say you can optimize this, but you need to be careful because of these subtleties that you're taking expectation values with respect to parameters that you want to optimize. OK.
So could you repeat how does the reparameterization trick help? Like what?
Yeah. So the problem is, say, take this term here. How could I go about maximizing this term? I want to take the gradient. So the first thing I might do is taking this full expectation is going to be too much. It's going to be intractable because this is a complicated distribution. The Q also is probably going to be a neural network. It doesn't have to be, but it could be. In which case, then you have to average all of the predictions that come out of this neural network. And so what you can do is you can take a sample of
So a neural network is deterministic.
yeah. So what you actually do if you want this to be a neural network is you have the neural network control the mean and the variance of a Gaussian, and then you sample from that Gaussian. But so I don't want to go into too many details here. What you would do is you would take a sample from that distribution and then evaluate this quantity. But that sample now has the parameters in it. So what you can do is you can pull out the parameter dependence from the noisiness of the sample, and then you can take the sample and then have the z be some function of that noisy sample plus the actual model that you're working with, and then you can take the gradient directly. Let me tell you more offline because yeah, I want to get the central idea across without the details of how you implement it. Okay, so the objective is to maximize this evidence lower bound. It actually has a pretty nice interpretation also. So the first term here, what you're doing is we're querying a particular x. We want to know log p of some x. What you do first is you encode it. You go from x to z using q, and then you go from that z that you just got back to x using your model. And that's why this is called an autoencoder, because you're taking a sample, you're mapping it into z space, and then you map it back to x space. And this is telling you how likely the model thought that the x was given the value of z that you sampled from the x with your encoder. The second term is essentially acting like a regularizer. It emerges from this sort of variational approach of putting in a q of z given x, but it acts like a regularizer in the sense that it tries to make q of z given x for every value of x be the same, or be close to, in terms of KL divergence, to this p of z, the prior of z. And oftentimes when people use these models, they just set p of z at the beginning. They don't learn it. It's just a fixed thing, some multidimensional Gaussian. And what this is essentially doing is it's trying to make your encoding of x into z space not kind of lose as much information as possible about the x. So it's trying to make that distribution of where you're mapping kind of generic, whereas if you went on the opposite limit, where you just mapped each x to an individual z that was completely distinct, you'd be just memorizing samples, and you wouldn't be doing any sort of compression that is going to be useful for actually learning something and not overfitting. That's the intuition behind this equation. And that actually leads into the last point that I wanted to make, which is that this objective function here is quite nicely related to something that has found good applications in biophysics, which is called the information bottleneck. How many of you have heard of the information bottleneck in the past couple of weeks? Stephanie talked about it. It's on.
It's going to be on the T-shirt.
Okay. Okay, good. So this is actually doing a version of the information bottleneck, and at least to my mind, using the information bottleneck in its original form is fraught with all sorts of difficulties, because you need to know the full joint distribution. Optimizing these informations is difficult. And it turns out that there are variational approximations to the information bottleneck objective that give you something very similar to this, that make everything tractable. And so there's a nice paper by Alex Alemi and co. called Deep Variational Information Bottleneck from a couple of years ago, which I think is goes a long way to making information bottleneck-like objectives really viable with big data. So let me just remind you, And I'm going to use, unfortunately, a slightly different notation than Stephanie used. In the information bottleneck, we have some variable x, which is going to be our input. There's a variable y that is the thing that we care about, and every sample of x is going to be correlated in some way with a variable y, in the sense that there's a joint distribution of x and y. And what we want to do is we would like to compress x, in a sense, into something called z. I believe Stephanie probably used t, but as I was saying, everyone in machine learning uses z for latent variables now. So we'd like to compress x into some z that's simpler in some sense, that still preserves predictive power about y. So the kind of objective function that you write down is, and here I'm going to deviate from how information bottleneck is usually written down again to be consistent with the deep variational information bottleneck paper. We're going to write down an objective which has the mutual information between y and z minus a parameter times the mutual information between x and z. And the difference between this and how it's usually written is there's a minus sign and the beta is in a different place. So be careful when you try and compare. So now here we would like to have a model that turns x's into z's while having as much information about y. So we want this information to be as large as possible, and we want this information to be as small as possible. So in principle, you can take the functional derivative with respect to this encoding q and use a sort of iterative algorithm called Blahoid-Arimoto, which if everything if you had the exact joint distribution and you could actually implement it, will give you a local optimum of this objective function. But in practice, this doesn't work very well for big data sets. Let me also mention that I wrote a paper a couple of years ago on a variant of this objective function, and I never found a good exposition of doing that, doing the sort of calculus of variations here. There are a few subtleties. So in the appendix of that paper, if you're interested in how this works, we had a page and a half of lots of equations that work all this out. In the general case that has as a special case this information bottleneck. So I recommend looking there if you want to see how this works. But I don't want to go there today. What this deep variational information bottleneck paper did instead was to say that you can actually get a bound on this, which looks like this. Imagine I have a data set of a bunch of samples, of capital N samples. Then you get a nice bound on this objective function that we want to maximize, which looks almost identical to what we have over there for the variational autoencoder. So you have a term that looks like an average over samples of this first term here, except that when we go from x to z back to x, we don't actually go back to x, we go to y here. Because our goal in the information bottleneck is not to just reconstruct the x, it's to predict the y. So this becomes a sort of supervised version of the variational autoencoder. And then there's a second term, which is beta times 1 over n sum over I of the KL between P of z given xi q of z. And this plays the analogous role to this KL here. One of the big exceptions, of course, is that there's a beta here, and there was no beta in the variational autoencoder. So in principle, you should put beta equals 1 if you want to have a direct connection back to this probabilistic framework here. But this objective function, by putting a beta in here as if this were a regularization term, and it was like a lambda that you put in and you varied the strength of and looked at performance. This has been studied in the machine learning literature, and it's called a beta VAE that is a very popular model anyway. So it's interesting that there's this really intimate connection between the approximations that you make to try and fit a model like that in terms of using this elbow and these similar kinds of variational approximations that allow you to optimize the information bottleneck objective. So I have about 8 minutes left. That was everything I wanted to tell you about unsupervised learning that even accidentally tied back to supervised a little bit. But maybe we should take some time to ask questions about this or anything in general.
So life's the universe and everything.
Life, universe, and everything. Yeah.
With the RBS, you had to estimate FIX from the model, and that was the slow part, the training.
Uh-huh.
And in the VAE, so there's an estimation term of the quarter part of PX given Z. But estimation there is somehow quicker than the other estimation because we are just taking a lower bound.
So the estimation is fast here because so I wrote this in general, where I didn't say anything specifically about what these Q's and P's are. But what's usually done in practice is this P of X given Z, which is called a decoder because it goes from the latent space to the data, is a neural network. And then the Q is also related to a neural network in that, there's the mean, you assume that Q is a Gaussian, and there are neural networks that control the mean of the Gaussian and the variance of the Gaussian, and then you can sample from that. So you can run through the neural network, get those values, and then you can sample from a multivariate Gaussian very quickly. So it allows you to do fast sampling. Yeah.
Maybe you said this, what is the motivation for unsupervised learning? Why do you do that?
Sometimes it just is the thing that you're interested in. Maybe you want a generative model that can produce new samples that have a similar statistical structure to what's in the data, but are not exactly just the same in memorizing them. It may be that you would like to have a supervised problem, but your data as it comes out does not have labels, doesn't have Ys. And you have to hire a graduate student for the summer to label them, right? And graduate students are way too expensive. So you would like to be able to do unsupervised learning and get as much juice out of that while maybe using a little bit of labels in the future, so you only have to hire one student. So there are many different reasons. You might also want to take apart the model once you've learned it, if you think it's a good model, and try to understand something about the structure of your data. From it, you might look at different experiments and see how your model is, the model that represents the data out of different experiments is changing as you change some parameters of your experiment. I don't think there is any one answer, though. Questions about life? All right. Well, thank you.